So this QR code is a link to a website, earthnullschool.net, which is what I've got up here. So if you weren't quick enough to get that QR code, just earth.nullschool.net. And it's an awesome website. If you haven't visited it, you should. So it's looking like it digests reanalysis as most recently as it can get its hands on, and is able to show a whole bunch of different fields in a sort of nice, neat, intuitive way. So that was what we were just looking at then, was sort of it was surface winds from like earlier today. This one is, ocean surface, and you can kind of straight away see like the different scales of motion and that sort of thing. You can zoom in, have a look around. It's a very cool website. So I'll go back to air, and instead of being at the surface, I'll move up to about 500 hectopascals, which is maybe about 5 kilometers up in the atmosphere. And the air up there looks quite different to like the air at the surface. And one of the most striking kind of features of the air at that height, at that altitude, are these waves. So this is the southern hemisphere, like the Jetstream, and these waves that are sort of present on that Jetstream are Rossby waves, and that's what we're kind of interested in. These are continental scale waves that really govern the weather that we experience, certainly in sort of southern Australia, and affect every aspect of our daily lives, from where we live to where we grow food and where we collect water and where we can generate energy and all that sort of stuff. So that's what it is that what I'm going to be talking about, these Rossby waves. So I'll just drop that down and all right. So before we get like into Rossby waves, I just want to cover 2 concepts just very quickly. The first is standing waves. So and to do this, we'll just go through a bit of a thought experiment. So imagine we've got this flow down a channel, and it flows here from the left of the screen to the right of the screen. And we've got a flow speed of u, and it's just a nice regular flow. And we can make a wave on that flow, and the wave is going to be, trying to propagate to the left. Okay, so if the wave speed is faster than the flow speed, so if the flow is moving slower than the wave is able to propagate upstream. Okay, so if the opposite is happening, so if the flow is going faster than the wave speed, then the wave is going to be vectored downstream. And then if the wave is equal to if the wave speed is equal to the flow speed, then that wave will just remain stationary where it is. So that's a standing wave. Okay, so in turbulent systems, like the atmosphere, or many of Earth systems, typically waves occupy all wavelengths, or many wavelengths, and sometimes these waves will travel with a wave speed that depends on their wavelength. So given that you've got a spectrum of wave lengths and a spectrum of wave speeds, chances are there's going to be one particular wavelength that has a wave speed that's going to be equal and opposite to the flow speed. So that if you take a long time average through this system, what survives that averaging process is going to be waves that are at the critical wave speed, and they'll have this very specific wavelength. Okay, so this time averaging allows us to kind of see through all of that turbulence and just really pick out those standing waves. And one of the neat things about these kind of standing waves is that they're kind of like an attractor for energy. Like energy is able to accumulate, a lot of energy is able to accumulate at these specific wavelengths, at these specific length scales. So yeah, when we're talking about standing waves, that's what we're kind of talking about there. So the second concept, I mean, also, it's my opinion, but most of the interesting stuff in Earth's climate happens when a wave speed matches a flow speed, and you're able to actually get these standing features and standing waves, and you're able to concentrate energy at these wavelengths and certainly scale energy up from smaller scales up to these particular scales. So that's standing waves. The second concept I want to briefly cover is potential vorticity, which you can really think of as just the spin of a fluid. So if we can imagine another thought experiment here where we've got like a puck, like a disc of fluid, which has got some thickness and some diameter, and then imagine that fluid is spinning. And it's spinning about its axis. So if you look at like the periphery of that disc, it might have a speed of u out here. And we can quantify the spin of the fluid. So this fluid, it's spinning relative to its surrounds. And so we would call it, we would say that it's got relative vorticity because it's spinning relative to its surrounds. And we can quantify that relative vorticity by considering the change in the speed of the fluid over the diameter of the fluid, like the distance over which it's changing. So here it would be, we've got it flowing at u on this side, and on this side it's going to be flowing at minus u because it's opposite to what's at the other side. So the change is like 2 times u, u minus u over the diameter across this disk. So we can come up with a way to quantify what the relative vorticity is. And if we take that disk, like that puck of fluid, and we actually stretch it in the vertical, what we're going to do is increase the thickness of the fluid. So we're going to change the height of the fluid, but in bringing that fluid that's sort of wide and further away from the axis of rotation inwards, we're going to be increasing the spin, like increasing the spin of the fluid at the same time that we're decreasing its diameter. So if we consider what we're doing to the relative vorticity when we stretch a fluid vertically and increase its thickness, we're increasing the change in speed across the fluid, and we're also decreasing the diameter of the fluid. So in terms of what we're doing to the relative vorticity, we're going to be increasing that relative vorticity. Okay, but the amount by which we're increasing that relative vorticity depends on how much we change the thickness of the fluid. So through a bit of geometry and maybe some conservation of angular momentum, you can probably convince yourself that the change in the relative vorticity, or this ratio between the relative vorticity and the thickness of a fluid, as you kind of stretch it and make it tall and narrow, and then squash it and make it short and wide, this ratio is going to be conserved. And so we can actually go back and forth between like these two different states of rotating like fluid and conserve this ratio of the relative vorticity to the thickness of the fluid. So we're going to keep that idea and we're going to build on a little bit because we care about fluids that are on a rotating sphere, like our Earth is a rotating sphere. And it's, Earth is rotating. The fluid on Earth, this means that the fluid on Earth is always spinning. Even if it's stationary relative to Earth, it's still spinning. So the spin of the fluid on Earth depends on where it is on Earth, like the latitude of where it is. And to cover that just very quickly, we can think of it as, Earth is here, it's spinning in this direction. It's spinning from west to east, so that if you're over here, the sun is always rising in the east. If we look at Earth from the southern hemisphere, we could have a look here and to us, it would, like if we're looking down on Earth from the southern hemisphere, it would look like Earth is rotating clockwise. If we were to do the same thing from the northern hemisphere, it would actually look like Earth is rotating anti-clockwise. So when you consider like what the spin of Earth is it's going to go from strongly clockwise at the South Pole to strongly anti-clockwise at the North Pole, but it changes smoothly and it actually goes through zero at the equator. So this change in the sort of spin of Earth, or is what we sort of call the planetary vorticity, and this is a concept that depends on the latitude of where you are on Earth, and it goes from something that's strongly clockwise at the South Pole and strongly anti-clockwise at the North Pole. By convention, we would call it F, which is the Coriolis parameter, and by convention, this is negative in the southern hemisphere and positive in the northern hemisphere. Okay, so we're going to take that concept that we've got this planetary vorticity and incorporate it into what we've sort of thought about in terms of stretching and squashing of the fluid. So we go back to this idea that the ratio of the relative vorticity to thickness is conserved. What's actually important here is the absolute vorticity of the fluid. So the absolute vorticity is the sum of the planetary vorticity and the relative vorticity. So this absolute vorticity depends on where you are, what your latitude is. And so if we incorporate those two ideas together, we end up with this an expression for the potential vorticity, which is the sum of your planetary vorticity and your relative vorticity divided by the thickness of the fluid. So this gives us a three-way balance. If we change one of these terms, we need to change one or both of the other terms in order to conserve potential vorticity. This dynamic potential vorticity is a materially conserved quantity, which means that it's if you're a particle of fluid, your potential vorticity needs to be conserved. For you to change your potential vorticity, you need a mechanism to do so. So I need a source or a sink of potential vorticity to change it. So with those two concepts in mind, standing waves and potential vorticity, we're going to have an attempt to look at Rossby waves. So we take Earth, we consider what the planetary vorticity is on Earth, and we know that it's a function of the latitude. So we have these lines of equal potential vorticity that circumscribe Earth. And if we think of a column of fluid at some particular location on Earth, and it's got some height, got some spin, if we perturb that, if that fluid is perturbed and moved, say, northward, it's going to be moving to a region of smaller planetary vorticity. So it's a different F, it's a different planetary vorticity there, where the magnitude of that F is closer to zero. Once it gets there, that fluid has excess relative vorticity. So its spin is different, it's anomalous to, and that's going to cause the fluid to be sheared by its surrounds and return, encouraged or pushed back to where it came from. So it's going to initially get bumped north, say, experience some shear with its surrounds, but then encourage that fluid to return back to the latitude that it came from. But as it's returning back to this latitude, it's actually carrying anomalous relative vorticity, because that's the term that's been changed while it's being north. So once it gets back to where it came from, it's still going to be anomalous relative to where it came from. And so it's going to continue to track south, tend south, and overshoot where it initially came from, move to a region of larger planetary vorticity. Then once it's there, it's going to actually experience it's going to get there with a deficit of relative vorticity. And in order to conserve its potential vorticity, it's going to experience a shear that is opposite to what it experienced when it was north. And so that's going to encourage that parcel of fluid to track back to where it came from. But it doesn't have a mechanism to actually slow down its sort of latitudinal progression here until it overshoots where it comes from. So we end up with this system that kind of just oscillates back and forth between zero, where it initially was, where it got perturbed to, and then back and forth in sort of north and south in latitude space. So anytime that fluid gets perturbed northward, it's got excess relative vorticity, and it experiences a shear that is in one direction, one particular direction, that is and being returned southward. Once it's perturbed southward, it's got the opposite anomaly in relative vorticity. So it experiences the opposite sense of that shear and returned northward. So when you look at those two kind of shears either side of the initial latitude, and you think about what the rectified effect of fluid being sheared in this direction north and fluid being sheared in this direction south is, fluid that's at the initial location is always being sheared to the west. And so this is the mechanism that planetary Rossby waves are, by which they're generated. They're encouraged to be to flow to the west. And if you add that westward shear, like that rectified effect, into this idea that they're actually going, they're oscillating between north and south, add those up, and you end up with a parcel of fluid that's actually moving sort of in this kind of wave-like propagation to the west. Okay, so as I've described it just then, this is, it's as if you're a single parcel of air, a Lagrangian tracer, if you like, of air, and you might think of, if you're a balloon, of having this kind of trajectory when you're riding on Rossby waves, and you might think of that as like being idealized as a figure skater that's able to conserve their angular momentum when they sort of bring their arms in and increase their speed, but added to that a little bit of extra, like the ice is sloping or something like that, that's able to actually give us a background gradient in the potential vorticity, the planetary vorticity. But that's not, like, this is too simple. That's not actually what it is like in reality. In reality, the fluids are continuous. So the original fluid that was actually perturbed north gets replaced by other fluid that's sort of coming in from other regions. That fluid ends up being anomalous as well and experiencing this process. So rather than it being a single parcel of air that's moving, what's closer to reality is that these are entire like slabs of air masses that are just kind of trending, tending north and south. They're entire weather systems that are sort of much larger scales, and are sort of in this kind of inherent mess of just chaotic fluid flow in the turbulent fluid in the background. So rather than thinking of it as a figure skater, it would probably be more like a mosh pit, where if you're in a mosh pit and it's crazy, everyone's spinning. There's a lot of craziness happening. The entire, like, there's structure in the pit, like there's structure to this madness, and certainly that you could probably certainly describe the crowd as having some sort of wave property. But yeah, I would say this is probably a closer analogy to what you'd expect than a figure skater. So planetary waves are a consequence of this conservation of potential vorticity. They're always propagating westward, and you can go through the exercise for convincing yourself that that's the case for the northern hemisphere. They always propagate westward. They occur on all possible length and time scales. So the perturbations, there's some connection between the perturbation scale and the scale at which they propagate, but it's loose. So let's just call it that they can exist on all possible length scales and time scales. So they can be the size of Australia, or they can be the size of like individual parcels, or the size of an ocean basin. And their wave speed is a function of their wavelength. So given that they exist on all these length scales, and the wave speed is a function of the length scale, the longer waves will tend to propagate faster than the shorter waves, which gives us this spectrum of wave speeds, so that if you've got a eastward flow, it's going to provide a mechanism for planetary waves of a specific wavelength the opportunity to actually become stationary. So, you'll have, because you've got a spectrum of wavelengths and a spectrum of wave speeds, there will be some wave speed that matches the flow speed, so that we're actually able to generate these standing waves in this background eastward flow. So if we go back to like what we were thinking about initially, like these are these waves that are propagating, the waves are propagating to the west, and you kind of see that they do peak up, but they're propagating on a background flow of eastward, that's on the eastward flowing jet. So if we try to model these waves, they're actually really tricky to model, because their dynamics span such a wide range of dynamical space. So one of the easiest ways and most efficient ways to do it is actually to use a lab experiment. Here you can clearly see that there's scales, like dynamical scales, on all on a very wide range of time scales and length scales that are able to be represented in this case, and we're with this approach able to span a wide range of parameter space and very quickly and efficiently sort of get through and start to explore, like, test hypotheses and explore ideas of like why, what happens, like what happens when this wave breaks. This is something that we can't do with numerical simulations at the moment, feasibly. Other questions that we can ask: what happens when the temperature gradient that drives these jets changes? What happens when the seasons change? How do these Rossby waves behave when you're going from a summer state into a winter state, and then back again? So I think that's where I'm going to leave it, and happy to take questions if there are. I haven't seen if there's anyone coming through online.
There's a few questions so far. But yeah, thank you for your talk and breaking down all of that really complicated physics for us. Again, for people online, the link to the questions is in the chat. You want to put your questions in there. But first question in here is, how does energy get stored in standing Rossby waves? Where does it come from? Where does it go?
Yeah. So what the perturbations are, doesn't, like, there's any number of different perturbations. Like you could have so convective processes could get energy into the system. Just day-night cycle, like the fact that the Australian continent heats up as the oceans either side of it is a way of getting energy into the system. The energy, I guess, is going to be coming from the latitudinal gradient, like the meteoritic gradient in temperature, which will have a lot of potential energy associated with it. So these, you'd have like these sloping isotherms at those heights that are able to actually sort of store a lot of energy. Where the energy is coming from is like all over the place. But what's neat is that, like, the energy that's like waves will, like, Rossby waves will get excited and they'll start to propagate, but there's these limits in the system that the slow waves will get wrapped up into these big waves and accumulate all of that energy from those smaller scales into this particular scale. Or alternatively, faster propagating waves will sort of get stalled at these at locations where the phase of this system is locked, so that you actually end up with like energy getting sort of funneled into these particular scales. Was there another part to that? Where does it dissipate?
Yeah, where does it go?
Yeah. So when these waves, like, I mean, if you look at this, these waves have a huge amount of potential energy, and it's at a wavelength that is enormous. Like here, it's the size of the that would be the size of Australia. How much energy is in that particular feature? Where it goes is it needs these waves to break, and if you've got a huge amount of energy that's at that scale, and the dissipation process is, well, I'll show you what the dissipation process looks like in the lab. So this is an experiment where we're actually very gradually changing the speed of the system so that it's not like a constant steady state the whole time. It's actually going from a fast state, which is here in wave number 5, to a much slower state, which is going to be around about here, where it's going to be sort of wave number 9. Okay, so here, this is a seasonal cycle. So we're going from one season to another. We're changing the peak at where the energy is, like from something that was peaked at wave number 5 to something that's now wave number 9. And that's going to require us to break some waves. So here's a wave that's about to break. Okay, that's the dissipation. That's where the energy is going.
Sure. The next question is, are there any similarities to oceanic Rossby waves?
Yeah. Yes, there are. The main difference is the scale separation. So in the ocean, the Rossby waves there are like this wavelength in the ocean. The wavelength of Rossby waves is closer to the sort of the deformation, the barometric deformation radius. So in the ocean, you have this this overlap between Rossby waves and ocean eddies that you just sort of call barometric eddies. The ocean also has a lot more topographic waves. So I've only spoken about planetary waves, and when you go back to any one of these ones, say like this guy here. In the atmosphere, this is the term that dominates, planetary vorticity. In the ocean, the depth of the ocean changes heaps. Like it goes from 0 to 4K, and there's continental shelves. So you can actually get a lot more overlap between what we'd call a planetary Rossby wave, which is a wave that's riding on a background gradient in planetary vorticity, to a topographic Rossby wave, which is one that's riding on a background gradient in the thickness of, like, the depth of the fluid. So in the ocean, there's Rossby waves. They're kind of mixed between planetary Rossby waves and topographic Rossby waves, but their length scales are closer to the background geostrophic length scale. In the atmosphere, the geostrophic scale is quite a bit different. Like the geostrophic scale is like we look at that. We're thinking about something that's the scale, like the size of these storms, versus something that is quite a bit bigger. So there's this scale separation between Rossby waves and the geostrophic turbulence in the atmosphere.
Cool. How does the seasonality changes of the Rossby waves affect Australia's seasons?
Yeah, awesome. Great question. So if we look at January, this is January, and this is like what January Rossby waves look like. Like the Jetstream is sort of further south. these, the amplitude of these waves are quite different. If we take a look at like a few months before then, the wave pattern there is quite a bit different. If we go actually to properly into winter, the wave's going to be different again. So the seasonality changes how many of these waves are able to actually exist around around Earth, because it's changing the location of the jet. It moves it to a different latitude, which has a different circumference around Earth, so it can fit more waves in. It changes the speed of the jet, which is going to change, which is the dominant, like the length scale that is stationary. Seasonality also can change. Yeah, it has a yeah. I'll leave it there.
Yeah.
Yeah.
Okay.
We don't have that many more questions, so maybe if anyone wants to submit some more questions, you can write them now. You can also yell out. Otherwise, I might ask you, mention that waves can get phase locked. What does that mean? How does that happen?
Awesome. So in the lab, we drive the waves with this bit of topography. And if you watch that bit of topography, the jet is always predominantly moving south, underneath that bit of topography. It might be easier in a different view. So we would say at that point there, the phase of the wave is locked to that piece of topography. And in the southern hemisphere, the phase is generally locked to the Andes. Like it's the only significant piece of topography in the southern hemisphere that is able to actually sort of encourage the waves to have it's the wave generator, if you like. This is where the waves start and they decay as they move downstream. The northern hemisphere is completely different, and it's probably stalled a lot of our understanding of Rossby wave dynamics because there's three massive pieces of topography in the northern hemisphere that phase lock these waves. So there's the Himalayas that really lock what the Rossby waves are doing at that point. The Rocky Mountains in North America, and then the Alps and sort of just the continent of Europe that is able to actually sort of influence where these Rossby waves are. So in the northern hemisphere, the Rossby waves are predominantly wave number 3 because there's three massive pieces of topography that lock the system. If the jet in the northern hemisphere flips and goes south of the Rockies, like Texas gets snow, and that's a big deal. Yeah. So yeah, so much of our understanding of Rossby wave dynamics has come from trying to understand them in the northern hemisphere from observations, which in the northern hemisphere they're not free. In the southern hemisphere they're free to adjust their dynamics based on the rate at which they're energizing or rate at which they're dissipated. But in the northern hemisphere it's topography locked. It would be nice to get a couple of extra pieces of topography in here and kind of demonstrate that, which I will eventually do.
Cool. Do we have any other questions online or in the room? Yeah.
I do.
I'll just yell out, say, Kyle, that's the best explanation of Rossby waves ever heard. Awesome, thank you.
Do you feel like you need equations?
Well, I'm happy there weren't any because that's the explanation you normally gets just all equations, but this was good to actually get a feel for it, a bit more intuition for it. So awesome.
Yeah, okay.
Well, I was thinking during those seasons when you have jet shifted northward, closer to Australia, does it mean that we would have like more frequent weather changes over Australia?
Yeah, yes. Yeah, you have more so yeah, the weather is like riding on the propagation of waves across Australia.
Yeah.
And so like, Michael Barnes's weather regimes, a lot of those are just phases of the waves. So a lot of there's different categories, and you kind of step through those different categories, and what they're doing is just propagating waves across Australia. And so if the propagation speed across Australia changes, that'll influence how the weather passes across Australia. There is some point in the year, probably twice a year, where you might think it rains every weekend, and it does, because the propagation speed has matched our 7-day cycle, so that it will rain every weekend, if it locks up in that particular way. But the interesting thing is that, or one of the interesting things is that there's like background flow speed that will give you a particular wave, like the theory will give you a particular sort of wave dynamic. When it's transitioning from summer to winter, and that same state will happen when you're transitioning from winter to summer. But the weather in autumn is very different to the weather in spring. Even though the background state should tell you that it's the same. Because one way you're taking energy out of the large scales and putting it into small scales, and in the other season you're putting energy from the small scales into the large scales. And the system is very different at those two. And we don't have theory for that. We don't have maths to tell us how does a system change from wave number 5 to wave number 9.
Can I ask a nice question?
Please.
So I spent 2 months in Boulder. That snowed every Wednesday.
Cool.
With a few variations, but you just said that the waves in the Northern Hemisphere are locked to the Rockies. So how are you getting that 7-day wave progression happening there if they're phase locked to somewhere in particular very nearby?
I have no idea. I mean, Rossby wave breaking accounts for, I can't remember the number, it's like 75% of rainfall in over Victoria, for instance. So there's 25% that isn't.
Yeah.
Yeah. I don't know what's driving weather in.
Oh, it felt like the waves were phase locked by how regular they were. So like not phase locked, they had shifted into the weekly cycle. I'm just curious how that's syncing up with the weekly cycle aligns with having phase locked to a mountain nearby.
Yeah, I don't know. Yeah.
But couldn't they still be locked to the Himalayas and just ignoring the Rockies at that point?
Possibly.
If the perturbation from Himalayas is stronger.
I was wondering if they were sneaking around the other side of the Rockies every time a wave came across.
Yeah. What season was it?
February, March, April. Mostly February, March. It broke by but it was a lot of weeks in a row, the same weather.
Yeah.
That'd be ideal for skiing.
It's fantastic for going climbing on the weekends.
Okay, we might leave it there. Thank you, Kyle, for your talk.
No worries.
And thank you, everyone, for sticking around. We are going to try and keep on doing these episodes every month or so. And our next one we have lined up is Gemma, who's in the room with me, is going to be teaching us how to use X-ray or DOS or something along those lines.
Something along those lines.
So look out for that.